Number 64. The hydrolysis of the sugar sucrose to the sugars glucose and fructose, which is this equation. So we have C12H22 plus O11 plus H2O, yields the glucose, which is always C6H12O6, and fructose, which is always C6H12O6. So they both have the same molecular formula, same empirical formula, but if we did look at these molecules, what they look like, they would look differently. But anyway, this reaction follows a first order rate law for the disappearance of sucrose, which looks like this. It's the rate equals K times the concentration of sucrose. And they say here the products of the reaction, which is glucose and fructose, have the same molecular formulas but differ in the arrangement of the atoms in their molecules. Wow, we just talked about that. But anyway, let's keep going. So for letter A, it says in a neutral solution, the rate constant K equals 2.1 times 10 to the negative 11th per second at 27 degrees Celsius and 8.5 times 10 to the negative 11th per second at 37 degrees Celsius. From that information, we need to determine the activation energy, the frequency factor, and the rate constant for this equation at 47 degrees Celsius, assuming the kinetics remain consistent with the Arrhenius equation at this temperature. Oh boy. Okay. A lot of stuff going on. We need to solve for three things for letter A: activation energy, frequency factor, and a new rate constant. But we got this. We'll take one step at a time. Now, the first thing is we want to find out that activation energy. Now, activation energy is always a EA value. So I say to myself, how am I going to get an activation energy from rate constant values and temperatures? Now, if you do see that you have two pairs of rate constants with temps, which is exactly what we have here, maybe let's label them out. Let's say that we have pairs of K1s and T1s, right? Capital T is temperature. So I have a K1 of 2.1 times 10 to the negative 11th, seconds to the minus 1, which is the unit for this K value. And then we have a T1 of 27 degrees Celsius. And then we have a new pair of rate constant with its temperature. So we'll say K2 equals 8.5 times 10 to the negative 11 seconds to the minus 1. And then T2 is 37 degrees Celsius. If I have two pairs of K1s and K2s and we have to find an activation energy, there's only one formula, and it's pretty easy, especially if you have a TI-84 or an 89. It's this formula right here. It looks intimidating, but I promise you it's not, because the calci is going to do a lot of the heavy lifting for us. So, we already talked about K1s and K2s and T1s and T2s. We have those pairs already. The idea is that we need to solve for EA, which is our activation energy. So we're going to label that as X. And the only thing that we didn't talk about is the R value, but the R values are constant numbers. This is 8.314, and it's in joules per mole times Kelvin. So that's the first thing I see here, is that if the R value is in a unit of Kelvin, those temp values that they gave us, right? Because they gave it to us in Celsius. So the first thing we got to do is just convert these Celsius values into Kelvin. But we can always convert Celsius to Kelvin by just, and maybe I'll put it up here, Celsius always to Kelvin is just adding 273, or being more specific, 273.15, which is what I'll do just to get a more exact answer. So 27 plus 273.15, we get 300 for our first temp, so 300.15 Kelvin. And then the other one, 37 plus 273.15, we get 310. 310.15 Kelvin. And now we're ready to plug in our K1s and K2s, T1s and T2s. Let's go for it. So we have ln of K1, which we said was 2.1 times 10 to the negative 11th, divided by the K2, which is 8.5 times 10 to the negative 11th. And I'm just making sure that those numbers are right. Yes, everything looks good so far. Equals the EA over R, so X over 8.314, okay, and then times by the 1 over the first temp minus 1 over the second temp. But just know that how I used to memorize this formula is that if you said K1 first, the other guy comes first. So it's like swapped. So it's K1, T1, and then T2, T1. So now I'm going to put the T2 one first, the 310.15, and then we're going to put the 300.15. Okay, so now here comes Calci. Calci is going to do most of the heavy lifting, because if you have a TI 84 or an 84 plus CE, which is the one that I have here, or an 89, or if you have any other graphing calculator, you should be able to do a couple of these steps at once. So what I'm going to do first is I'm going to plug in all of this in one shot. If you feel more comfortable, doing the division first to get one number and then press the ln, that is fine with me. Your answer should come out to being the same thing eventually. Gotta love it when it rhymes. But anyway, we're going to press natural log ln of 2.1 second comma times 10 to the negative 11th divided by 8.5 second comma times 10 to the negative 11th. Close that up, just making sure that everything looks good. Looks good to me. And we get that one number now, negative 1.398 equals, next one, this division, can't really do much with that right now because it's tied in with that variable, so I'll just leave it like that. So x over 8.314. And now, Calci's also going to do the heavy lifting for this. We can plug all this in one shot into the calculator. But if you feel comfortable finding out what this is, doing the subtraction, you can always do that as well. Your answer should come out to what I get. So 1 over 310.15 minus 1 over 300.15. Looks good to me. And 310 goes first. Yep. Negative 1.07 times 10 to the negative 4th. And that's this guy. All right, so let me bring this up a little bit, because what we can do is we can now just simplify this, make it into one fraction, because I have two numerators here. I have the negative 1.07 times 10 to the negative 4th, and then I have the x value. So we can multiply these two, and it could be on the same numerator. So what I'll do is maybe I'll split this, and I'll say negative 1.398 equals negative 1.07 times 10 to the negative 4th times x over 8.314. Now we're back to just, cross multiplying it out, dividing just to get that answer. I could cross multiply these two values. So I'll take the exact number. So it's going to be this number times 8.314. That looks good to me. So negative 11.62 equals negative 1.07 times 10 to the negative 4th times x. Divide on both sides by negative 1.07 times 10 to the negative 4th. And then, there we go. Cancel that one out. And now we get x equals, which is the activation energy. So let's see. This divided by this number. Beautiful. So maybe we'll do, 2 sig figs, 1.1. 1.1 times 10 to the 1, 2, 3, 4, 5. And just know that these units are going to be in the other units of the R value. So joules per mole for right now. That's why it's so large. This is joules per mole. So if you wanted kilojoules, which this question, let me just make sure, did this question ask for it specifically in kilojoules? They just said, determine the activation energy. So if you wanted, you could just take this number and divide by 1,000. So you could say either 1.1 times 10 to the 5th, or you could say 110. So maybe that's what I'll do. So for my EA value, it's either going to be 1.1 times 10 to the 5th joules per mole or 110 kilojoules per mole. Okay, and that's the first part. So what I'm going to do is I'm just going to color this in, and then we're going to move on to the second part. Let's see which one is going to be easier to solve for right now. I know that we have to get the frequency factor. And then the next one after that says, oh boy, this is getting a little bit nuts. Oh, that's nice. Okay. Then the next one says we have to find a specific rate constant at another temperature. So I think what we're going to do is we're going to bypass this for now, because I noticed that the next one is they want us to find a rate constant at another temp. So that's kind of going with the same exact idea here, that we need to pick one, K1 or, K2, and now we're solving for a new rate constant. That's going to be using the same formula. So what I'm going to do is we'll save this one for later. I'm going to solve for a rate constant, K. So now maybe what we can do is we could keep one of these. So maybe what I'll do is maybe we'll keep this K1 and K2. But now we're just going to change our K2 and T2, right? K2 is the one that we're solving for. A rate constant is always K. So that's going to be now the X value. And T2 is going to be that temperature with that rate constant. They said now that this is going to be 47 degrees Celsius, but the issue that it was before, we just have to convert the 47 into Kelvin. So let's do that. 47 plus 273.15. Okay, so we're going to be dealing with 320.15 Kelvin. Okay, so now using the same formula, the X value is not going to be the EA, right? It's going to be K2. That's going to be the X value. But now, what are we going to plug in for EA? Yeah, we're going to plug in what we just found out. For a formula, or for a balanced equation, your activation energy is going to be constant. So it doesn't matter what K values and what temperatures you're using, that activation energy is going to be the same. Now, since the R value is in the joules, we have to use the joule value. So we're going to use 1.1 times 10 to the 5th joules per mole for this one. Okay, so what I'm going to do is we're going to get rid of this math. So just pause the video if you need to. We have the EA up there. And I'm going to get rid of this. And I don't know what's going on outside. Maybe they're cutting down a tree. But if they are, hopefully it doesn't fall on me. Oh, gosh. Okay. Anyway, we're going to just manipulate this a little bit, because the K1s and the T1s are the same, so the reds stay the same. The only thing that's changing are the blues. So we're getting rid of this K2, and we're plugging this in as the X value. And then we're getting rid of this blue value, and we're plugging it in for 320.15. And now you can, instead of solving for X over here, we now know that that X value is 1.1 times 10 to the 5th. And just like we did before, where we blocked these three things off, you can do that as well. So for now, the first blocking, right? This, I can't do anything with this because the X value now is in the natural log. So that's just going to be ln of the 2.1 times 10 to the negative 11th, and then for X equals do the second blocking. This we can now do because it's just a number over a number. So we're going to do 1.1 second comma times 10 to the 5th divided by 8.314. And we get a large value, 13230.7. So that's that guy. And then we can do the third blocking, right? Just like we did before. So 1 divided by 320.15 minus 1 divided by 300.15. Let's just make sure that these look good. 320, that looks good to me. And now that's just one number, negative 2.081 times 10 to the negative 4th. So now in this case, we can actually multiply these two numbers out. How fun is that, right? So we're getting there. We can't do anything with this yet, so we'll just bring that on over here. So ln of the x value on the bottom, the k value on the top, 2.1 times 10 to the negative 11th, equals now, let's multiply these numbers together. So I'm going to take this value and times it by this value. Negative 2.75, right? Yep. And now we're ready to get rid of that natural log. What's the inverse of natural log? Yeah, it's e to the. But if you do that on one side, you got to do it to the other side. E and natural log are inverses, so now you're just down to 2.1 times 10 to the negative 11th over that x value. And that's going to equal, let's see, we're going to say second ln, that's the e value, and I'm just going to take the whole number here. So I get 0.06, I don't know, 0.6, I'm just going to write a couple of numbers down, 37. And now we're almost there. Let's just maybe bring this up a little bit. Cross multiply, bring that x on over. You could probably see what we're doing now. So it'd be 0.0637x equals the 2.1 times 10 to the negative 11th. And now just divide on by 0.0637 on both sides. Okay. And then that gets rid of this. Now we're going to finally include that 2.1 second comma times 10 to the negative 11th divided by this whole value. And there we go. X, which was, maybe I'll make it in blue, because this one was the K2, right? That was the rate constant. And we'll say 3.3 times 10 to the negative 10th. And the unit here is the same units as all the other K values, so seconds to the minus 1. And I will box that answer off and I'll throw it up on the top. And we're done with that one. Okay, 2 out of the 3 questions done. Whew, this is getting nuts. But now the reason why I did these 2 first was because once you talk about frequency factor, the formula changes. So this is where we're going to be using that Arrhenius equation. So just pause the video if you need to write anything down, because we are now shifting gears. We're going to a completely different formula, so we can say bye-bye to this formula. So let's just get rid of all this. Yeah, I guess let's leave just the 1K value here, but all this is now going. Say bye-bye. We have all the answers on this side anyway that we need. And let's get rid of that. Okay, so shifting gears. Now, whenever I see frequency factor is always, so maybe I'll put that over here. Whenever you're seeing frequency factor, that's always a capital A. I guess A for Arrhenius, because this is the Arrhenius equation. That's why in the last formula, right, did we see any A values? No, that's why we weren't using that one. But here is the formula. Whenever you see that you need to solve for a frequency factor, it's this right here. There's that A value. And now for your Arrhenius equation, you only have one set of rate constants with temperatures. So it doesn't matter which one you choose. If you want to use these guys, go for it. If you want to use these guys, go for it. I don't want you to get confused that, don't look at these colorings and say, oh, 1K has to be coming from here, 1T's got to be coming from here. These, what I'll do is I'll make these the same color. It was just that when I made this formula, I used different colors, and then maybe we'll do EA in blue. Doesn't really matter. Okay. So pick your pair that you want to go with. The K value here, let's do these, right? And I just realized that I just got rid of the temperature here, so I'll just put that back. This was 2.1 times 10 to the negative 11 seconds to the minus 1, and we just have to convert that into Celsius again, so this one was the 300.15 Kelvin. We need Celsius, we need Kelvin again because there's that R value. We know that the R value is that constant number. It's the 8.314 joules per mole times Kelvin. So there's that Kelvin. In this case, the T value is going to be the 300.15 Kelvin. And the EA, remember, for any reaction, the activation energy is going to be the same. Since the R value is in the joules per mole, let's use the joule per mole EA value. So 1.1 times 10 to the 5th joules per mole. The A value is what you are searching for. So that's the X value, and this E value is the E on the calculator. So it's on Calci. Now, let's plug it all in and see what we get. So we're going to say 2.1 times 10 to the negative 11th equals our X value, and then it's E raised to, oh boy, maybe I'll box it off after I write all the numbers. So it's going to be E raised to the negative 1.1 times 10 to the 10 to the 5th, and then we have 8.314 times the 300.15. Okay, now what you're going to do is let Calci do all of this in one shot. Get this to being one number, right? So I'm going to say negative. The negative's in the formula. 1.1 second comma times 10 to the 5th divided by 8.314. And now since I'm not using parentheses, I'm going to press divide again to get that number in the denominator. But, you can get these numbers to being one number and then do the division. It doesn't matter to me. You should get the same number at the end. Okay, so we got 2.1 times 10 to the negative 11th equals that frequency factor, which, by the way, frequency factor is just basically telling you how frequent the number of collisions are happening in this reaction. Anyway, let's keep going. So it's going to be E raised to the negative 44.08. So the next thing that you're going to do is literally do E raised to the negative 44.08. So we'll go over here now. 2.1 times 10 to the negative 11th equals X times whatever that value is. So we're going to say second ln EE raised to that whole number. It's going to be very small, but that's okay. When you divide now by a really, really small number, you should get a really, really big number. And that's exactly what we're going to be doing here. We got to divide by the 7.18 times 10 to the negative 20th. 7.18 times 10 to the negative 20th. Your frequency factor should never be negative. So if you do get a negative, just go check yourself at the end. And let's see, now I'm going to bring in that 2.1 times 10 to the negative 11th divided by this total number. And there it is. I guess we'll say 2 sig figs. So my A value, which is my frequency factor, equals 2.9 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8. And the units for your frequency factor is the same as your K values. So whatever the K value is, that's what the frequency factor is. In these, it was first order, so this is just seconds to the -1. So this is just basically saying that, per second, there's a frequency of, 2.9 times 10 to the 8th collisions with these molecules. I mean, there's so many molecules going on in these containers. They're just bopping up against each other. But we did it. Whew! If you are here, thank you so much. I really hope this helped. Thank you for staying for the 3-hour and 27-minute video. But we did it. We have the activation energy, the frequency factor, and that new rate constant. So it's all here. All right. So thank you so much. I really do appreciate you guys. I really hope that this helped. Let me know in the comments. I try to get back to you as much as I can in my free time. But thanks so much. Thanks for being part of the community. And if you guys are on the playlist and you need letter B, just stay, right? I'll see you in a few seconds. And enjoy your day, okay? Keep studying hard, and I'll talk to you soon. Okay, bye-bye.